Hi, this is Ms. Fitzmaurice. This video is an explanation of the problem on page 26 of your Unit 7 packets. This is also problem 3 from the 2004 Physics B test. So in this problem we have a vibrating tuning fork, much like the ones you've used in class, and we have a tube full of water. And there are two places, or two water levels, L1 and L2, where you are able to hear a resonance. So you put the tuning fork on top of these columns and you can hear a sound. We know that the first time is when L1 is equal to 0.25 meters. And we know the second, L2, is at 0.80 meters. Okay. We also know that the speed of sound in air at this temperature is 343 meters per second, and that the speed of sound in water is equal to 1490 meters per second. Alright, so for part A, it wants us to find the wavelength of the standing wave. Okay, so the way we're going to do this is we're going to look at the difference between these two lengths. Okay, because we don't know exactly what harmonic either of those are, right? There could be several half waves in here, or maybe because water is not a totally hard surface, some of the sound waves are coming into the water. We're not going to get a really clean-cut boundary where we know we have, exactly 1/4 of a wave, or exactly 3/4 of a wave. But we do know that probably whatever happens at the boundary should be the same at water level. And so if these two, L1 and L2, are successive harmonics, then they should differ by exactly a half wavelength. Okay, so for part A, to find the wavelength, we know that half of a wavelength is equal to the difference between L1 and L2, so that's 0.8 minus 0.25 meters. Okay, and we can use that to calculate a wave, and we get the wavelength is equal to, so we get a wavelength of 1.1 meters. In part B, it wants to know the frequency of the tuning fork that produces the standing wave. Okay, so if this is true in air, then we can use V equals lambda f to find the frequency of the tuning fork. Okay, so in air, our velocity is 343. Our wavelength is 1.1 meters. We're calculating frequency. We get frequency is equal to 311.8 hertz, or 312 hertz. Okay, in part C, it asks us to find the wavelength of the sound wave produced by this tuning fork in water. Okay, given that the frequency is going to be the same. Okay, so once again, we can use V equals lambda f. We have our frequency from before, so our frequency is going to be, and I'm going to round to 312 hertz. Our velocity is the speed of sound in water, so that's going to be 1490. And we're solving for wavelength, so when we solve that, we get lambda is equal to 4.78 meters. So it's actually a much longer wavelength. D says that the water level is lowered, and so we hear a third resonance, and we want to know what is L3. So as I said, we don't know exactly the shape of the wave when it is on its boundary with the water, but we know that for each harmonic we're adding half of a wavelength. Okay, so if L1 is at 0.25 meters, and it sounds like, you know, maybe it has not quite half a wave, then let's say this is L1, and L2 is an additional half wave. L3 should be an additional half wave, so that we have exactly a half wave between each one. So we have 0.25, and then we have 80, and then the difference between those two is 55, so L3 should be an additional 0.55 meters past L2, which ends up being 1.35 meters. Okay, so we should get L3 is equal to 1.35 meters. Alright, and then part E says, the student is performing this experiment, determines that the temperature of the room is actually slightly higher than 20 degrees C. Okay, so if your room is slightly higher than 20 degrees C, it turns out that as temperature increases, the speed of sound increases as well. Okay, so it asks us, is the calculation of the frequency too high, too low, or still correct? And so we have to think about the equation. We used V equals lambda F. Okay, our lambda should still be correct, right? But our velocity, our estimate was too low. So if our velocity number was too low, our wavelength was correct, then our frequency should also be too low.